In this assignment, we will be dealing with the way the camera moves. In order for the controls to work correctly, the camera will need to be mainly pointing in the positive world Z-axis. This means that when the user presses the up key, making the player move positively in the Z-axis, this will translate to an approximate up direction of movement on screen. We are also going to point the camera slightly negatively down the X and Y axes. This shouldn't harm the feel of the controls unless we point the camera too much in either direction. To get a view that we're happy with, position the scene camera looking at the player as the main camera should do. Something like this. Once you've done this, highlight camera_main, and from the Game Object menu, choose Align with View. You should now see in the game view that this matches our scene view camera. You can now move the scene view camera to wherever you want. Now that our camera is aligned, let's make the script to control its movement. Add a new script component to camera_main and call it CameraMovement. Double-click the icon for editing and then clear the script. We will only need one public variable in this class, a float that will affect the smoothness of the camera's movement. As for private variables, firstly we need a reference to the player's transform, so that we know its position. We need a few more private variables. So that it's easy to tweak the position that the camera tracks the player from, we're going to store the position of the camera relative to the player. We need to store this in a vector 3. When the player moves behind an obstacle, we want the camera to pan upwards so that we can still see the player. Thus we will be creating more positions for the camera to potentially be in. To make sure that these other positions are the same distance away from the player, we will need to use the magnitude of the relative position vector. Rather than calculate this every frame, which is expensive, we will store this magnitude inside a float variable. Once we have calculated the new position for the camera to move to, we will need to store it so that we can lerp between the camera's current position and this new position. Now we can use the awake function to set up our references. First we need the reference to the player. The relative position of the camera from the player is the camera's position minus the player's position. For the relative position's magnitude, the distance of the camera from the player, we're going to make a slight adjustment, reducing it by a small amount. This is because the player's position is at his feet. Thus, when we want to raycast to the player to see if anything is in the way, we will hit the ground if we don't reduce it slightly. For the camera, we will be using the fixed update function to update its position. This is because, although it is not a physics object, it will be following a physics object. In order to get the movement as smooth as possible, both the updates will need to happen at the same time. Now we need to store all of the potential positions of the camera. We will start off with the standard position of the camera, which is just the player's position plus the relative camera position. Next, we store the position of the camera when it is looking directly down on the player. This is the position of the player plus the magnitude of the relative camera position in a direct line upwards. Now that we have the standard position of the camera and the position of it directly above the player, we need a few positions in between. We will organize these positions into an array. This will make looping through them to check which position the camera should choose much easier. If we have the standard position, the above position, and 3 positions in between, then we will need an array of 5 vector 3s. These will be points at which we check if the camera can see the player, so we will call the array checkpoints. The first of the positions we want to check is the standard position. To find the positions between the standard position and the above position, we are going to use the lerp function in a slightly different way than you might have seen before. What the lerp function does is returns a value which is a percentage between the two values it is given. At which point between the two values it returns is dependent on the third parameter. At 0, it will return the first value. At 1, it will return the second value. If you have a value between 0 and 1, then lerp will return a value some proportion of the way between those two values. For example, Given two vector 3s and a third parameter of 0.5, lerp will return a vector 3 halfway between the two. We are going to use this method to find positions 25%, 50%, and 75% of the way between the standard position and the above position. The last position in our array is the above position. Having found all the points at which we want to check if the camera can see, now we can loop through them to see which one works. We will make a function that checks these positions and sets the new pos variable when it finds one that the camera can see the player from. This function should return true when the camera can see the player. We will be using a raycast from the position we're checking and then seeing if we've hit the player or something else. So the first thing we want to do is to create a raycast hit so that we have something to check. Now we perform the raycast and see if it hits. We want the raycast to start at the position we're checking and head in the direction of the player. We want to get the information from our raycast hit, and we want the length of the raycast to be the distance of the player from the camera. Given that the raycast has hit something, we want to now check if the transform of the thing that we hit is not the player's transform. If it is not the player that we've hit, then we can't use this position, so we return false from this function. If we didn't hit anything with our raycast, or we did hit something but it was the player, then the position that we're checking is appropriate for the camera, so we can set the new pos variable and return true from the function. Now we need to call our function from within our loop. We also need to consider what happens when we have found the correct position. If we leave the loop to continue, then it will find the last position which is appropriate, which is always going to be the above position. So when we find the first appropriate position, we need to break out of the loop. We do this using the break keyword. The break keyword simply exits whatever loop it is placed in. It works in a similar way to the return keyword in that it jumps you out of the code that you're in, but while return works for functions, break works for loops. Now we have a new position chosen for the camera, we can lerp its position between the current position and the new position. Now that we have the camera moving to an appropriate position, we need to make sure that it's actually looking in the right direction too. An easy way to do this would be to use transform.lookAt. However, because this would point the camera at the player every fixed update, it would actually appear jerky whenever the player is moving around, because it is overly precise. Instead, we want the camera to smoothly catch up with the player when they move. So we're going to create a smoothed lookat function instead. We are going to use a similar method to how we change the player's direction based on input. We're going to get a vector 3 that points from the camera to the player, and generate a quaternion from that. This is going to be the rotation that we want the camera to have. Once we have that, we can lerp between the camera's current rotation and the proposed new rotation. To start with, we're going to need a vector from the camera to the player. Next, we use the look rotation function that we came across in the player movement script. This will return a quaternion to represent the rotation of the object whose forward vector is given. We also need to supply an up vector to make sure that the camera is the correct way up. Finally, we can lerp the camera's rotation between itself and the new rotation that we've generated. The last thing we need to do with this script is put a call to our smoothed lookat function. Now that the script is finished, save it and return to the editor. Again, we're going to tidy up our scripts folder. Open Scripts in the project panel and drag Player Health into the Player folder. For camera movement, we're going to place in a new subfolder. Create one called Level Dynamics and then drag Camera Movement script into it from the Assets folder. Now let's playtest our scene. Click the play button at the top And as you can see, our character now runs around the level with the camera tracking him. You can see that as you get closer to the wall, the camera moves to the above position. And as you move further away, it tilts down, going to the percentage-based positions that are in our array. Remember that now we have the character moving, we can also trigger the alarms. Press play again to stop testing. Then finally save your scene and save your project. In the next assignment, we'll add the key to the level that unlocks the lift.